So at this point, we've added our retail sites over the WAN. Now we're going to explore how to build our factory network a little better. In the previous module, we leased the floor space. Now we're ready to start putting in some network devices. As is often true in manufacturing, maybe we don't have the expertise to build all of our product, but just a big part of it. Let's assume that we are sharing the floor space and a general LAN environment with a partner that's going to help us build this product. There are common resources that we both need to access. Maybe we've stood up a shared server inside the factory that tracks inventory and production schedules, and we need access to that. For the purpose of the diagram, that would be hosted behind R13. Now, the constraints for this problem are actually pretty difficult, so let's check those out next. The solution needs to be accessible from the campus, WAN, and partner. That means that all those different organizations need to be able to reach into the extranet to access the resources. Another important characteristic of most extranets is that we don't want any cross-network transit or internet transit across them. For example, if our partner's internet connection fails, that partner should not be able to route all the way through the network through SBC out to the internet. The opposite is also true. SBC shouldn't be able to use the partner's internet. They just need to share a common resource without transit. We also need to provide optimal routing to and from the extranet. So if you look, R11 and R12 both have connections into the extranet, but one link is clearly faster. We should always prefer R11 for traffic into and out of the extranet, using R12 as a backup only. The last constraint is a little more subjective, but we want to minimize OSPF knobs and new protocols. Let's explore some candidate solutions first and see if you can figure out why they might not be a good fit. One very common solution to extranets when you have OSPF on either side is to just use static routes. It's simple, it's clear, it's safe, and you're unlikely to have any suboptimal routing. Now in our case, when we do the redistribution on R11 and R12, we would just ensure that the R11 seed metric is lower so that that path was chosen, and on R13, we would have a lower administrative distance static route pointing to R11. This would ensure we have optimal routing, and again, it's not that hard to implement. The problem is that it scales poorly, so if the extranet grows and there's more subnets within the extranet, maybe we add a bunch of new server VLANs behind R13, then we need new static routes all the time. We also need to manage those static routes on R13, so if SBC adds some new retail sites and maybe it doesn't fit within the company's IP block, it doesn't fit within the aggregate, then we need new statics in the extranet too. And as I said earlier, we would need explicit metrics on all the static routes on R11 and R12, which is another knob we generally want to avoid. For a more dynamic solution, we can use BGP. Again, this is another very common approach. We get a lot of control, it's obviously highly scalable, and we overcome a lot of the problems with static routes. The drawback is that there is a lot of upfront planning and config. We would need to identify AS numbers, route filters inbound and outbound, maybe even communities, path prepending, local preference. There's a lot there we would need to think about and implement. This is probably a gold-plated solution, meaning it's overkill for the problem we're trying to solve, and that makes it not a great candidate. We would also need explicit metrics for the redistribution on R11 and R12, and because we're doing redistribution with a dynamic protocol, we introduce the possibility of route loops if we do it incorrectly. We could also use another OSPF process for the extranet and basically just do mutual redistribution on both sides. This is a middle ground approach because we get pretty good control, not quite as good as BGP, but we also don't have to introduce new protocols. However, this is probably the greatest risk for suboptimal routing as we have redistribution in at least 3 different points, and this is definitely going to get sloppy. There's also the highest risk of misconfiguration in this network. We could get our process IDs wrong. I'm sure we've all typed in the wrong OSPF process ID and accidentally enabled wrong OSPF processes on our routers before. I know I have. There are just a multitude of things that could go wrong in this design. So is there an easier way? Is there some way we can do this without violating any constraints? In this specific business environment, consider using an NSSA area inside the extranet. This is a not so stubby area, which is a type of stub, but it has some interesting characteristics that make it a good fit for this particular design. This approach is simple and it's safe and it's scalable. It also gives us good control at the border routers on what prefixes come in and which ones go out. You might be wondering which routers are the border routers because we clearly have a disjoint area 0. From the very beginning of our OSPF indoctrination, we're taught that this is a bad thing and we should try to avoid this, and now you might be thinking we have some kludgy GRE tunnel or something like that. No. There is nothing wrong with having a disjoint area 0 if it's planned and part of your overall strategy. The same is true for IBGP. A lot of people think that you need to have a full mesh and you need to have route reflectors or you need to have confederations. No, it depends on your topology. You may not need full connectivity. In this design, we're not going to have any routing loops because it's all just OSPF, and OSPF puts in the safeguards that will prevent connectivity where we are specifically trying to prevent it. We don't need to deal with any explicit metrics on R11 or R12 because OSPF is running on those links inside the extranet. So core area 0 is going to know what the best path to enter and exit the extranet is going to be. The solution is a little bit tricky to wrap your head around, but if you're able to discard your preconceptions and your long-standing opinions about OSPF design, you should be able to grasp it fairly quickly. It's important to remember that the NSSA is a type of stub area, which means we can never have external routes flooded into it. This means that there will never be a default route inside the NSSA unless our ABRs explicitly originate it. This is a good thing because it will prevent any internet transit between the two partners. Remember that disjoint area 0s cannot transit a non-zero area to talk between themselves. This is normally framed as a bad thing, but that is precisely what we want in the extranet design. From the perspective of the extranet, it can reach any network because all the internal routes are allowed in. R13 should have a full view of everything in OSPF, both from the partner and from the core, but it's not going to have any external routes. That's exactly what we want. This does not require any fancy filters or redistribution or route maps or any craziness. When we look more closely at the outbound routes, we see that we also have a lot of flexibility. We can use internal routes, so for example, having LAN segments off of R13 that are just advertised into Area 3 directly, that's perfectly fine. We can also do redistribution because it's an NSSA, so we can redistribute from connected, or maybe there's a BGP connection off R13 or whatever. We can do redistribution and originate NSSA external routes inside the NSSA. If you look on the right side of the screen, you'll see we have an internal route, which is 10.0.0.13/32. That's fine. We also have an NSSA external route, which is, in our case, redistributed from connected, which is 10.13.13.13/32. When these LSAs reach the ABRs, regardless of whether it's the partner or the core, the action's going to be the same. For these internal routes, the ABRs will originate a summary LSA, which is inter-area, and flood that to the rest of area 0. They'll also translate the NSSA external into a regular external and flood that as well. What makes this fun is that on the right side of the screen, we get a quick look into lots of different OSPF route types, which makes this kind of interesting and a good way to summarize what you know about OSPF in a very small, condensed network. Let's explore the NSSA in greater detail on the command line so you can see how the pieces fit. Let's start on R13, which is inside the extranet, and check its OSPF interfaces. According to the diagram, this router should have 4 different neighbors on 4 interfaces, and we can clearly see that it does. Notice that all interfaces are in Area 3, including loopback 0, but there's another loopback, which is loopback 1, that is redistributed from connected. We can confirm that by checking for locally originated NSSA external LSAs in the OSPF database. We can see that the route is 10.13.13.13/32, and it was originated from R13. This prefix should be translated to a Type 5 LSA at the border routers, which are R11 and R12, back into the SBC core area 0. Let's test connectivity into the NSSA using these 2 prefixes all the way from R9. If you remember from the previous module, R9 is one of our retail sites far across the network. Let's traceroute to 10.0.0.13 to see which path it takes. Looking at the diagram, this appears to be the best path, so let's quickly trace it by checking the fib and rib routes along the way. We already know that R9 and R10 have static default routes pointing up to R8, which gives us scale over the hub-spoke network. Let's go to R8 next. Outside of the WAN environment, each router should have the specific /32 for that route. All the Area 0 routers are going to see this as an inter-area route learned by a Type 3 LSA originated by R11 or R12. R8 sends the traffic to R1, so let's go there next. R1 forwards the traffic towards R11. You might be wondering, why didn't R8 pick R2 and then send it to R12? That's because OSPF is smart enough to try and avoid that serial link on R12 because it's very slow. We won't get into the low-level graph trace on exactly how that happens, but if you think about the total path cost, it should make sense intuitively. Finally, let's check R11. As expected, it's intra-area, and it goes directly to R13, which is the end of the path. So we just traced an internal OSPF route, which is a mix of intra-area and inter-area routes in the routing table along the path. Let's go to R9 and test connectivity to the external prefix next. We'll traceroute to 10.13.13.13. The routed path through the network is the same, but we'll see that the routes along the way are completely different. R9 sends traffic upstream to R8, so let's check that next. You can immediately see some differences between these two show commands. The first time we had an inter-area route, but this time we have an external route. We can see the next hop is still R1, but the originator was R12. The NSSA has an interesting feature where traffic can flow through one ABR, but the LSA for it can be originated by a different ABR. R12 is part of the NSSA control plane, which just originates the Type 5 into the non-NSSA areas. R11 still remains the best forwarding path, and again, behind the scenes, it's a little tricky, but there's a forwarding address inside the external LSAs that help tell the routers where to send the traffic. I detail this in my troubleshooting OSPF session, which is much more advanced, so if you'd like to understand how that works better, you can search for that other session. Let's go to R1 to continue tracing this path. R1 is still sending traffic to R11, and this is still a regular external route. No surprises here, but let's go to R11 and see what changes. Inside stub areas, you can't have external routes, so the NSSA external is a way to bend the rules and allow external routes without actually having Type 5 LSAs. Remember, in our environment, R12 performs the translation, but R11 is clearly in the routed path. That wraps up our quick look into NSSAs and extranets. I've used this design a few times in real life for some pretty complex customer environments. I'd invite you to explore more, and again, check out my troubleshooting OSPF session if you want to dig a little deeper. In the last module, we're going to cover tuning OSPF in service provider environments.